Okay, so let's begin with some probability theory. Let's first start by asking what a probability actually means. Now, this may seem very basic, but there's different interpretations that we can have. So let's start with an example of a classic example of a coin flip, where the probability of a coin landing heads is 0.5. Now, how you would probably interpret this is that half of the time that you flip the coin, it's going to land heads. However, that interpretation is not actually very applicable to AI and in general to prediction tasks. And I'll give you one example. Let's say we're predicting, or we're essentially not even predicting, we're just looking at what the weather app says for tomorrow. And let's say the weather app says that there's a 50% chance of rain. That means that the probability of rain is equal to 0.5. Now, we see that these are both the same probabilities. The probability of heads is 0.5 and the probability of rain is 0.5. But you're not going to interpret rain as, oh, in half of the tomorrows or 50% of the tomorrows, it rains. Because that's not possible. There's only one tomorrow, right? So what we're really interpreting this as is that the 0.5 is a representation of the uncertainty that we have. It's a representation of the uncertainty of the prediction. And so what we're really saying is that we believe there's a 50% chance of rain, and that means that there's a 50% chance of not being rain. And so you really have to look at probability as uncertainty. And we already saw in the last module with information theory how uncertainty is vital to machine learning. So let's just think of it that way for now. Okay, so what I have over here is essentially another weather example, right? Let's say we're talking about summer weather. Okay, so first let's start with omega. So the omega sign is standing for the entire sample space. So what the entire sample space consists of is all the possible outcomes, right? So in this case, during the summer, the weather's all possible outcomes are, let's say, rain, sunny, and cloudy, okay? It doesn't snow here during the summer, right? So this would represent the entire all the different possibilities. So the probability of omega, or the probability of the entire sample space, is going to be equal to 1, or 100%, because it is guaranteed that this entire sample space contains of whatever outcome is actually true, because this is all of the possible ones. Okay, now let's go over these sets over here, A, B, and C. Now, A, B, and C are all subsets of this sample space set. These are all subsets. Now, the reason why they are subsets is because in each of these sets, the element or elements can all be found in the broader set over here, the broader sample space set. So A, B, and C would all be referred to as subsets of this set. Okay, great. Now, let's go over a few more stuff. Specifically, let's go over the axioms of probability. So there's three main axioms. So the first axiom is this, right? It's that right there, that the entire sample space, the probability is equal 1. The second axiom is that the probability must always be greater or equal to 0, right? We can't have a negative probability. That just doesn't make sense at all in like the standard way that we think of probability. And then finally, the third axiom is this. So the third axiom is if two events are mutually exclusive, meaning, and mutually exclusive, by the way, what that means is that they cannot both occur at the same time, then the probability of A union B is equal to PA plus PB. Now let's go over what this means. So first, two events are mutually exclusive if both of them can't occur at the same time. So in this case, A, B, and C are actually all events, right? They're all events or something happening, right? That's why they're subsets. They're specific events, right? Now, what we see here is that A and B are clearly mutually exclusive, right? A and B do not share any of the same elements inside of their set. meaning both of them cannot occur at the same time. So what that would mean is that the probability of A union B, and by the way, union is essentially a combination of both, but without any repeating elements. Well, that's just going to be equal to the probability of A plus the probability of B. In this case, the probability of A is equal to 2/3, right? Because rain, sunny, cloudy, rain and cloudy represents 2/3 of that entire sample space. So probability of A equal to 2/3, and the probability of B is equal to 1/3, right? So then our total probability over here would be equal to, sorry, not 3, it'd be equal to 1. Okay, cool. Now, let's go over our next concept in probability. Okay, so our next concept here is going to be what's called the complement, right? And the complement, essentially in a, for example, subset over here or in an event, would be what is the probability of this not happening? So if I were to say probability of A, C, like this, right? What I'm asking is what is the probability of A, not happening or not occurring in the given context, or none of the elements of A being inside of this? Well, what this will be is just equal to the probability of the entire space, right, which is 1, right, minus the probability of A, right? And this goes for any set, right? This goes for any set. That is one of the rules over there with complements. Okay, now what we're going to dive into is the concept of independence. So what the concept of independence is actually telling us is that if two events are independent of each other, then the probability of A intersect B is equal to probability of A times probability of B. And I'll give you this example over here. Let's say we have 2 days during the summer, right? And let's say both days the weather is independent of each other. Now, obviously in the real world, we have tracking and we have different trends and stuff, but let's suppose both of these days don't have any influence on each other's weather. Well, that means that these events are independent of each other. That doesn't mean they're necessarily mutually exclusive, because both of them do share the trait of being cloudy. So they're clearly not mutually exclusive, and they actually do share an element. Instead, they're independent. So what you can think of this symbol as you can think of it as an and, right? What's the probability of A and B happening? And that's going to be equal to the probability of A times the probability of B. Now, in the given context of this, what would that be equal to? Well, that would be equal to 2/3, right, times 2/3, right, which is then equal to 4/9, right? So yeah, and essentially what this is saying is, what this is saying is that the probability of it either being raining or cloudy is 2/3, right? And the probability of it either being sunny or cloudy is 2/3, and because they're independent of each other, 2/3 times 2/3 equals 4/9. So that's going to be A intersect B, and the probability of that. This only works when the events are independent. Now, you might be wondering why the complement matters in AI and why intersection matters in AI. So let's first start with the complement, right? So the complement is very useful in any sort of binary classification task, right? Because in a binary classification task, you only have 2 possible outcomes. So the probability of one outcome is equal to whatever number you find, right? And the probability of that not happening is just going to be equal to the probability of the complement, which is 1 minus the probability of that event, right? And then as for intersection, it is clearly useful because, as we're going to see, this is then going to be used in Bayes' theorem, which kind of represents all of AI and how AI specifically learns, specifically how AI is able to adapt to new information.